evening, students. Today we will continue with this applications of electronic effects. Yesterday we completed stability of carbocations. Today we will see stability of carbene ions. In a carbene ion, there will be a negative charge on one of the carbon atoms. So in a carbene ion, this is the negative charge, and around this 4 sigma pairs of electrons means this is sp3 hybridized, and the shape of carbene ion is pyramidal. Now we will see stability of different types of carbene ions. So first we will take alkyl carbene ions. So alkyl carbene ion stability depends on hyperconjugation or plus I effect. So stability of alkyl carbene ions is inversely proportional to plus I effect and directly proportional to minus I effect. So more the plus I effect, lesser is the stability; more the minus I effect, more is the stability of carbene ions. Now we will take some examples. First we will take different alkyl carbene ions. I take CH3 minus. What is the name of this one? Methyl carbene ion. Next, ethyl carbene ion. This is a primary carbene ion. Ethyl carbene ion is a primary carbene ion. Let primary. Now I will take isopropyl carbene ion. It is a secondary carbene ion. Isopropyl carbene ion. It is a 2 degree, means a secondary. How do you say it is a secondary? The negative charge is located at a secondary carbon. A carbon which is attached to 2 other carbons is secondary carbon. So this is a secondary. Then tertiary butyl carbene ion. Tertiary butyl carbene ion is an example of a tertiary carbene ion. Now already you know that methyl groups show plus I effect. So if you observe this one, there is no other methyl group, means no plus I effect. Here 1 methyl group, here 2 methyl groups, here 3 methyl groups. Then from methyl carbene ion to tertiary butyl carbene ion, plus I effect increases. When plus I effect increases, stability decreases. Then we will take some more examples in this one. Substituted carbene ions will take. Already we discussed what are minus I groups, plus I groups in yesterday's class. Okay. Let this is a carbene ion. CH2 here, NO2, CH2 minus. CH2, CN, CH2 minus. Then CH3, CH2, CH2 minus. What is the nature of this NO2 group? It is a strong minus I group. Then this is also a minus I group, whereas this CH3 is a plus I group. Then what is the stability? With the increase of plus I group, plus I effect, stability decreases. So here stability of these decreases. This is more stable than this one, than this one. Now I will take another example. That is carbene ions in which other atoms attached to negatively charged carbon are with a different hybridization. We will take CH3, CH2, CH2 minus. Now I take this carbon. Around this carbon 4 sigma bonds means what is the hybridization of this one? sp3. Then I take CH2 double bond CH2 minus. Now I take this carbon attached to the negatively charged carbon. This is sp2 hybridized carbon. Then I take triple bond CH2 minus. This carbon is sp hybridized. You know that more the S character, more is electronegativity, En. Then a more electronegative carbon stabilizes a carbene ion. Then what is the stability order of these three carbene ions? This is the stability order. Stability. That is, more electronegativity of the carbon attached to negatively charged carbon, more is the stability. This one. Then I will take another example. I will take this CH3 C double bond O CH3. What is this one? Propanone. Later it is converted into a carbene ion. Propanone is converted into carbene ion. I take like this, CH2 minus. The nature of this CO is minus I. So among these two, if you take, this is more stable, it is stabilized. Like this, C double bond O minus. Here I take one more keto group, like this. I take another one, like this. C double bond O here, C double bond O here, one more C double bond O. This one. So here, what is the change you observe? This has only one minus I group, this one has two minus I groups, this one has three minus I groups. So here minus I effect increases, then stability of these carbene ions also increases. Then what is the stability order of these? This is. I think you understood. Now we will take in the same way in applications of electronic effects. Next one, stability of free radicals. In a species, if there is one unpaired electron, or you can say 7 valence electrons in one of the carbon atoms, then it is a free radical. Okay, before discussing this one, free radicals, we will see some benzyl carbene ions also. I forgot to discuss this one, now I will discuss. If you take benzyl and allyl carbene ions, the stability is directly proportional to resonance. That is, more the number of resonating structures, more is the stability. Already you know how to write stability resonating structures of ions. Let this is benzyl carbene ion. The stability depends on resonance. Here this electron pair involves in resonance. Like this we can write resonating structures. So this is one resonating structure, here a double bond is formed. Then in next structure this electron pair forms a pi bond here. Like this we can write resonating structures. Then this comes out as negative charge. So double bond CH2. Similarly in next structure this comes out as a negative charge. Then double bond CH2, CH2. Finally this is a structure. Now we will take allyl carbene ion. Allyl carbene ion is also stabilized by resonance. CH2 minus. This minus is nothing but an electron pair. So this is shifted in this direction. What is this carbene ion? Allyl carbene ion. Then resonating structure is CH2, CH double bond, CH2. This one. Okay. Now I will give you some carbene ions. You see what is the stability of these carbene ions based on number of resonating structures. C6H5, C6H5, this one. C6H5 minus C6H5 CH2 minus. What is the stability order of this? That you see. With the increase of number of rings, number of resonating structures increases, so stability also increases like this. Now, if we take this benzyl carbene ions, stability is directly proportional to minus M effect and inversely proportional to plus M effect, plus mesomeric effect. Yesterday we discussed. Then we will take a few examples of this substituted benzyl carbene ions. This is a carbene ion in which NO2 group is substituted at this one, NO2. Next, benzyl carbene ion. Next, here I am substituting methoxy group, OCH3. I am substituting methyl group, CH2 minus CH3. Now, this NO2 shows minus M and minus I effect. This stabilizes carbene ion. Here no group. Now, this OCH3 shows plus M effect and minus I effect. And this decreases stability of carbene ion. Here CH3 shows plus hyperconjugation, plus H effect, electron releasing effect. Electron releasing effect decreases stability of carbene ion. Electron withdrawing effect, electron withdrawing group increases stability. Electron donating groups decrease stability. So, what is the stability order of these carbene ions? This is the stability. So, in entrance point of view, stability of carbocations, carbene ions, free radicals, it is important. Now, we will see free radicals. Stability of free radicals. And stability of free radicals, again here if you take alkyl free radicals, stability is directly proportional to hyperconjugation, plus H. So, stability is directly proportional to hyperconjugation. Go pen తర్వాత ఎడిట్ చేస్తారుగా. So, stability is directly proportional to hyperconjugation. Now, I will take this is methyl free radical, ethyl free radical, methyl free radical, next ethyl free radical, this is a primary free radical, then isopropyl free radical. Isopropyl free radical is a secondary free radical. Secondary. Now, tertiary butyl free radical. Tertiary butyl. This is a tertiary alkyl free radical. And yesterday we discussed applications of hyperconjugation. Free radicals are stabilized by hyperconjugation. More the number of alpha hydrogens, more is hyperconjugation. So, if you take here, this is alpha, this is alpha, this is alpha, here alpha, alpha, alpha. Then number of alpha increases. So, number of hyperconjugative structures also increases, or simply hyperconjugation increases, then stability of these free radicals also increases. This one. Now coming to stability of benzyl and allyl free radicals. The stability of these free radicals depend on resonance. Benzyl and allyl free radicals. Stability is directly proportional to resonance. Stability, resonance. Now I will take one example. Already you know this one, how to write resonating structures. Okay. Yesterday we discussed how to write resonating structures of free radicals. With that you can then another secondary benzyl free radical. This is secondary. Then tertiary this is tertiary. Then number of resonating structures increases or simply resonance increases, stability increases. Stability increases. So this is the stability order. Like that of in carbocations, even in benzyl free radicals also, an electron donating group increases stability and electron withdrawing group decreases stability. So if you take similar examples, that is I take this benzyl free radical. Now at para position I am taking fluorine. Here I am taking chlorine. And here I am taking say bromine. Halogens attached to aromatic ring show two effects. One is minus I effect and another one is plus M effect. So here it is also minus I and plus M. Minus I plus M. So if we take based on minus I effect, the stability of these free radicals, let this is 1, 2, 3, 4. Then which is more stable? One is more stable. Here by considering this minus I effect, halogens, fluorine has more minus I effect than chlorine, bromine. Then 4 greater than 3 greater than 2. This is the stability order of benzyl free radicals. Similarly, you can see stability of allyl free radicals. Now another application of this electronic effects is acidic strength. We will take carboxylic acids, acidic strength of carboxylic acids. Okay. Already you know that acidic strength for strong acids Ka value is greater. Then this acidic strength, or before this we will see how do these carboxylic acids show acidic nature. This oxygen attracts electron pair in this direction, then H plus comes out. Compounds which release H plus are acids. Okay, greater the tendency to release H plus, more is acidic strength. Then based on this one, acidic strength is directly proportional to electron withdrawing effects. Electron withdrawing effects means like minus I and minus M effects. and this is inversely proportional to plus I and plus mfx, plus mfx. This is very important in entrance point of view, acidic strength of carboxylic acids. Okay, we will see some examples based on this one. If we take a very important comparison, that is acetic acid, formic acid and benzoic acid, formic acid, benzoic acid. Here this CS3 shows plus I effect, and whereas the C6H5 shows resonance effect, resonance effect. Because of this, here acidic strength order, formic acid is stronger than that of benzoic acid, but acetic acid is weaker than that of benzoic acid, CS3COOH. This is the reason. Now, we will take some more important examples by substituting different groups in carboxylic acids. For example, if we take formic acid, acetic acid, propanoic acid and butyric acid. With the increase of number of carbon atoms in alkyl groups, plus I effect increases. That you have to remember. More number of carbons, more is plus I effect. Then acidic strength decreases. We will take some isomers of carboxylic acids like N-butyric acid, CH2COOH, isobutyric acid, CS3, COH, N-butyric acid. This is isobutyric acid. Here these alkyl groups contain same number of carbons, but with increase of branching, plus I effect increases. Plus I effect increases means acidic strength decreases. So, you have to see when there are same number of carbon atoms in alkyl groups, the one which has a straight chain has less plus I effect than the one which has a branch. So, same number of carbons, more branching, more plus I effect, like this. This is important comparison. Then if we take some more examples like this, we will take some substituted benzoic acids, COOH. Here let it is NO2, dinitrobenzoic acid, trinitrobenzoic acid. What is the nature of NO2 groups? NO2 group shows minus I and also minus M effect. Minus I and minus M increases acidic strength. So, minus I and minus M increases, acidic strength also increases. Understood? So, this is acidic strength order. Similarly, if there is electron donating group, it decreases stability of carboxylic acids. So, if you take COOH here, let NO2, COOH benzoic acid, COOH here I am taking CH3. What is this compound? Paratolic acid, right? Then you see what is the stability order of these three. Okay, tomorrow we will continue with some more important tips. Thank you.
V3 న్యూస్ లక్ష్యం సమాజ హితం.
స్టడీ బడి V3 న్యూస్ స్మార్ట్ ఎడ్యుకేషన్ సమాజ హితమే లక్ష్యంగా దూసుకుపోతున్న V3 న్యూస్ సామాజిక సేవలో ఆదర్శంగా నిలుస్తున్న వైశ్య వికాస వేదిక సంయుక్త ఆధ్వర్యంలో విద్యార్థుల కొరకు మీ ముందుకు తీసుకురాబోతున్నారు స్టడీ బడి. వివిధ పోటీ పరీక్షలకు ప్రిపేర్ అవుతున్న విద్యార్థుల కోసం అపార అనుభవం గల ఫ్యాకల్టీలచే ఉచిత శిక్షణ మీకు అందుబాటులోకి రాబోతుంది. ఇందులో భాగంగా నీట్, జేఈఈ మరియు ఎంసెట్ ఎంట్రన్స్ కు జూన్ 29 నుంచి జూలై 31 వరకు ఫ్రీ కోచింగ్. స్టడీ బడి సోమవారం నుంచి శుక్రవారం వరకు మధ్యాహ్నం 3:30 నుండి సాయంత్రం 5:30 వరకు, తిరిగి సాయంత్రం 6 నుంచి 7 వరకు మీ V3 న్యూస్ ఛానల్లో, V3 న్యూస్ యాప్లో, V3 న్యూస్ యూట్యూబ్లో ప్రసారం అవుతుంది. యూట్యూబ్లో V3 న్యూస్ ఛానల్ని సబ్స్క్రైబ్ చేసుకోండి. అలాగే V3 న్యూస్ యాప్ను మీ మొబైల్స్లో ఇన్స్టాల్ చేసుకోండి. దశాబ్దాల